My name is Hoffman. I work for Cloudflare in the Linux SRE team. The topic that I'm talking about today is maybe slightly out of fashion for the modern world of the cloud because it deals with actual devices and with troubleshooting and forensics for the Linux kernel. Where you need it is if your task to administer is like either physical hardware or things like IoT devices where you control the Linux kernel and where you wish to have postmortem diagnostics from. So Crashdumps, what are Crashdumps to start with? Because it's not something that like even senior SREs stumble over every day. And so the easiest to illustrate what Crashdumps are is to compare them with the more well-known stuff of application core dumps. So when we have a system, a Linux system, which runs you a number of applications, however complex they are, if an application crashes, Linux will write you a memory image of the crashed application in the form of a core dump. You can afterwards open it in a debugger, use it for forensics on the application, find out why did it crash. You can put it into an automatic analysis pipeline that like feed it information into Sentry about stack traces, about like memory usage patterns and so on and so forth. So crash dumps are the same kind of thing, but not for an individual application. You get them when the system as a whole crashes, meaning when the Linux kernel encounters a condition that is fatal and will not be able to, and you won't be able to continue after it. You don't always get those on a Linux system. In fact, they're not like default. You have to configure them. So we should first look into how Linux systems in general use dumps. And the process is a bit more complicated than for application core dumps, because to get an application core dump, you configure systemd core dump, and application core dumps magically appear somewhere. For crash dumps, well, you have to do the same, except that the way the Linux kernel writes crash dumps is slightly different. Because so if the Linux kernel crashes, the system is in an inconsistent state. It's not quite clear what still functions, what's still safe to do. Say, for example, the disk device driver has crashed. Can you write to the disk and put a crash dump onto the disk? Maybe not safe. The other thing is if at the time the Linux kernel has crashed, you continue to execute complex code. You're modifying the memory that you're trying to save out in order to get your forensic snapshot. Another reason why you don't continue at those. So Linux crash dumps do something nifty. On crash, you actually kexec into the kdump environment, which is a pure init ramfs ramdisk root based Linux system. A new kernel that starts reinitializes devices, gets you the state, the system in a back into a good state, and eventually it runs the userland, which is the kdump procedural bit. And that part, all distributions do it slightly differently, yet quite similarly. They run a minimum init, whether systemd or classical init, which mounts the original host's root file system. The hope there is we'll do like log recovery, whatever, want this corruption or anything. We'll start that up with like a minimum config, possibly recover network state. We read the configuration file of the host at kdump.conf, which tells us where do we want to put Crashdump. And once we have that, we run the utilities that actually extract and write the dump with a little tool called make dump file. After that, we reboot normally and the ordinary host restarts. Now, this is nifty because we get the frozen system, we get a reinitialization of our devices, we share state between the host root file system and the kdump environment. So the kdump environment can look up where's my targets and so on. It's generally being considered reasonably decent. Now, what's the issue with this? Well, the issue with this is like what's unreadable at the bottom of my slide here. So if you want this to work, then the kdump environment, which is just a RAM disk, must have access to the root file system, like on stable storage. Now, there's the issue that we wanted to solve. I have a set of references on Crashdumps if you want to read up on it. They will go into the collected slides. So that's the issue that we want to solve. The classical kdump, no matter which distribution you look at, always uses this process. Init ramfs starts, tries to look at the host root file system, look for a configuration file that tells kdump what to do, and eventually write to the target. Now, what if we don't have a root file system because we're not booting from disk? Or we have a root file system that's encrypted, and we don't want to give the encryption keys to that kdump init ramfs. What if as a host root file system, we don't want to trust that kdump init ramfs, meaning, no, you're not gonna like even see any of my storage. It's none of your business, could have customer data in it. What if the dump system is on an internet exposed network, and we don't want any of the data on it to end up in someone else's hands, and so we use the host's network configuration to open that thing to the world and trust it where we write our dump. So we want to be a bit more careful, meaning we want a dump mechanism where the kdump environment knows nothing. It's stateless, and the information that we want should just be passed ephemerally. So as I said, the state here, there's a lot of state involved. Config files for kdump. Usually the kdump init ramfs is actually dynamically built by the systemd service that starts the whole thing. Well, secure boot, locked down stuff, whatever, dynamically building init ramfs, I'm not so sure. We boot the host, access the root file system, mount it. We write storage devices of the machine. We have, if we use network dumping, use access to the network configuration or to SSH keys of the host. This is all things which we potentially may not want. We may, in addition to that, not even have a local root file system. If our system boots ephemerally, if we run it off RAM disk, if we run it in a configuration where we always repave on reboot, then we do not have a file system that we can go to from the kdump init ramfs. If we have encrypted rootfs, we may not be able to access it from some ephemeral, untrusted environment. So, and the other thing, if we build the kdump environment at runtime, then, well, someone else can build a kdump environment at runtime. And it's a very nifty way as a sort of unauditable backdoor into your system by building an init ramfs with a busy box in and ability to access your network and just kexec that by crashing the machine. I don't want that to happen on my environment either. And the second thing, if I'm already making sure that my environment is like inaccessible and I've got secure boot configured and I've got IMA on, then kdump as it is in the old style doesn't work because I'm dynamically building in ramfs image. This is not signed because the signed keys aren't on the host. I can't trust it the same way. So my idea is I have to actually build the kdump environment that runs the dump off host, sign it the same way as any other executables that I want to run, transfer it on there. But in order to do that, it obviously cannot have host-dependent state in it. What we've done is something that works by probing. The usual way of the crashed system executing the kdump kernel starting devices and bringing up the kdump environment is the same. the reason why this part here is unaffected by secure boot, for example, is because we are just trying to k-exec the same kernel that crashed, and that is implicitly trusted. If we were able to load this kernel to start with, then we're able to k-exec this kernel from that kernel as well. So that part is fine in any case, as long as the two kernel versions, the two kernel images are the same. But this part here, we custom build, and we do very simple steps with it, because what we'll do is we have a custom little init script that just loads network device drivers, brings them all up, no matter how many network devices the box has, just mod probes them all and brings them all up, and then it probes the destination address. We pass the destination address via kernel command line to the thing. So state is ephemeral because it goes via kexec call to the kernel command line of the crash kernel, and from there into init. And if the destination address answers on the given network interface, we know we reached our dump source there. And then we run make dump file in curl. We can theoretically write with that to anywhere. But I mean, I just said I don't want to write anywhere. Now, because if I were to be able to write anywhere, then even with the lockdown thing, someone could still tell my crash kernel, write this to my chosen address. I would like to receive your dump. Kernel crash dumps are memory images. They're essentially system snapshots, not unlike virtual machine snapshots that are used for like suspend resume of a migration, but snapshots that are to be used for forensics. And they contain a lot of information, including potentially private sensitive, potentially security sensitive information. I don't want to send them to just about anywhere in the world. I want to send them to somewhere where I know they're not going far away. And so let's sum this up for the moment. What we do is we pass the config via kernel command line only. And what we need is few things. Some like keying information that says, okay, I'm this host, sort of. Some form of destination address information. And that is the only way how we pass state. The kdump init ramifest itself is pre-built. It's fully static. We can sign it with integrity protecting mechanism we want to use. What happens? Crash kernel boots, initializes the system, resets devices, gets us in a clean state, starts init, and the init will run the procedure that I just described. Now, it's not completely there yet because there is this network issue. So network actually has a lot of state, because if you try to play with it on a low level, in order to get a network device to talk to something, you ordinarily have to configure quite a few things. You have to bring the network device up. You have to set an IP address on it. You have to set a default gateway or some form of route or whatever on it that tells it how to reach the destination. You potentially have to configure naming services for it, because your destination might be behind some form of like DNS load balancing of sort. Ordinarily, DHCP hides this for you, and the config management, like network manager or however your config management system brings the network config up, does the rest of that magic. And when you're there, the world's your oyster. You can access anything. You can write anywhere. Like, so if anyone manages to insert you DHCP in the boot process, then your machine will happily talk to what they tell it to talk to. So the world might be my oyster, but I got a little bit of an upset stomach when I think about my Crashdump environment. Someone takes my box and presses the diag button, and it sends a memory image somewhere. So I'd rather not trust some external configuration to the network. But if I already need some form of configuration to make the network reach anything, how can I minimize that? How can I make sure that it really can't go to the world? And what we decided to use is IPv6. IPv6, unlike IPv4, actually has a built-in facility. When you bring the interface up, the interface will probe the network and send ICMP packets, ICMPv6 packets out to the router that say, hey, I am the following host. My IPv6 link local address is a special type of IPv6 address that is not routed, that will never leave your L2 domain, is the following thing. It's synthesized from my MAC address. Like, would you mind setting this up for me? So this is a mechanism which is standardized in IPv6, always has been. You'll see that working when you bring, like on Linux, some virtual adapters up. You just configure the network device, you bring the network device up, and you magically see an IPv6 address appear on it, like FEA0 : something. That's the slug address. And we decided to use this because it allows us to make sure that the kdump environment has a network configuration. It will never try to leave the local data center. It's always IPv6. So what we make sure is that we tell it to write to a linked local address. So let's say FEA0 : dead bodies, because that's where system corpses like Crashdumps should go. This is the mechanism which we can use to assure the Crashdumps don't go anywhere untrusted. The rest of the magic is done actually in using curl for our HTTP put request, because we bring a little service up here that listens on an IPv6 linked local address. It only needs to be physically connected via the same L2 domain to crashed machine. We tell curl in the dump environment, we give it the certificates for the service. So we make sure that it cannot write to, it will not trust writing to that service. Even if someone else brings that service up, they don't have the certs for it. So this curl will do the HTTPS connection to this one here, using the certs that it has built in. The private part is only on our service. So even if you take the box, rip it out, bring the address up somewhere else, unless you stole our private certs for this thing, it will not write the dump. And so you're not able to extract the memory image from our system unless like it's writing to our dump sink. And so that's the way how we secure this end to end, and how we make it possible for a machine that boots from network, repaves on reboot. We just insert an intermediate step that goes via kdump, writes the crash dump, if it finds the destination sink. Otherwise, you just go through the crash dumping process, fails to find the destination sink, and reboots ordinarily. Otherwise, it writes the crash dump. We get a memory image from the system crash. We can do our forensics. And after that, the machine goes into its normal reboot. I have a box prepared where I can just show how that looks like. It's relatively boring because you just see system messages scroll through. But before I show that, I would like to give you some chances to ask questions about this, because I understand it's a little bit of an esoteric topic. So if anyone wants to know something, please feel free to ask. So let's see if my demo actually works. So I've prepared a little virtual machine. Let's see if that's readable. So I'm starting this with a little systemd service, but the systemd service is primitive because all it does, it runs kexec. So where are we? So essentially, this is the only magic in it, where we run the kexec command and we tell it load the crashdump kernel. We give it an init ID. We say reset devices. We give it a few parameters, our crash sync IP address, the crash sync port number, we say host use systemd config and the Linux kernel file. And if I start this, no. What I've done is I've connected two VMs together. VirtualBox, the one that is running the Crashdump, and the other one is the dump sync one. I started a primitive HTTPS listener there. So that's got certs. It only talks HTTPS. It only talks a little bit of the obfuscating protocol that the Crashdump side understands. And so if I crash the box now, then we should see some effect here. So hopefully you see something. Okay. So, okay. It's nice. So it triggered a crash, but I might not have had my service running. Okay, let me power cycle this and do this again. I probably have forgotten to start my kdump service. I just boot this thing. It's relatively quick, so we have a chance to do another one there. Okay. Okay, yeah, so it's running now. It's enabled, so let's do the same thing again. There we go. So now instead of going through the ending at the crash, we actually go through the Crashdump process. So yeah, so we actually see some stuff happening here. Wonderful. And that's it already. So this went a little bit fast. You can still roughly see, because the dump output here writes what it received, what it got sent from the other side. So we send a Crashdump over. We say this is some application Linux Crashdump dmask, and the other one is the second one is the actual Crashdump image. So it's relatively fast on a VM. On an actual server, it can take a few minutes because it takes a lot longer to dump like 200 gigabytes than it takes to dump like 50 megabytes or what the VM dumps. The advantage here is this box, it needn't even be a physical machine. This can be something like a Docker image where you configure the IPv6 link local address on container local CNI configured interface. So you don't even have to share this with like your production environment. This could just be a dedicated receiver image that you insert somewhere, and is that the service knows nothing about it, but this is an IPv6 link local address where I write to. And I trust that the target of it has the certification that I require to trust it. Yeah, that's all. If there's any questions about how this works technically, how you can use it, how you could put it onto, say, an IoT device where you want to use diagnostics for, I can give you more background to this. And otherwise, the slides will hopefully be shared after the conference. Thank you so much.
Yes.
Yeah.
Demos don't usually
Yes. No, I tried demo earlier, and it actually didn't work in dry testing, but that is because the main VM runs network manager, which messes up IPv6 link local address setup. So the crash environment makes it work.